This is lecture 16, and in this lecture we're talking about assembly program. We're talking specifically about program flow and then about timers and I/O. Program flow is the biggest part of this though. Let's dig in. Program flow, timers, interrupts, input and output. That's what we're talking about here. So first we're talking about program flow. Program flow. Well, one direction of flow is the flow of data. We have our general purpose registers, and that allows us, we can move data around using the move command between one register and another. We can move data through I/O registers. Okay, through I/O registers, we can use in command and out command. Okay, so that's specifically for I/O registers, and there, when you choose a register, you actually need to choose the I/O address, not the memory address. Remember, there's a difference of 20. So this would be memory address 0023, but it is I/O address 0003. We can move data to the stack through the pop and push. We can put immediate values in, and we can also transfer data to and from memory. Data memory, program memory, and EEPROM memory. So there are different ways that data can flow, different directions, different places. In terms of program control instructions, we have conditional statements, we have unconditional statements. So the conditional, we have branches, and so we have a branch. So we have a bunch of different kind of branch instructions. We have a bunch of different skip instructions. So branch if equal, skip, I don't remember exactly what that one is. Then we have unconditional instructions like jump or rjump. We can do calls. We can do subroutine calls, an R call or regular call, and then we can do returns, like a return from interrupt. So a number of different program control instructions. So for a lot of the branching instructions, the status register is the thing that decides a lot of aspects of the branching. So the status register, again, just by way of review, this pops up all over the time, all over the place. It's a very crucial register, and so the I bit here is for interrupt enable or disable, 1 if enabled, 0 if it's disabled. T is a temporary storage bit for just a single bit. So if you have just a bit you don't know what to do with, you can stick it in the T register, the T bit in the S register, and then you can then grab that bit later. So the bit could be 0 or 1, depending on what you want it to be. So, but keep in mind, someone else might want to use that bit. So be careful. That is, if you have a interrupt service routine that wants to use that bit too, you just ought to be careful. Although the interrupt service routine probably ought to save the status register so that when it returns out of the interrupt service routine, the status register is intact from when it came in. Then there's the half carry bit. It's a carry bit from bits 3 to 4, from one nibble to the next. So remember, a nibble is half a byte. And this is primarily used for doing binary coded decimal arithmetic. That's kind of an esoteric function, very infrequently used. But anyway, it's available. There's the signed bit, the S bit, which basically is the N bit exclusive ORed with the V bit. And this is used a lot for signed branches. So this is actually very commonly used for signed branches. We'll come back to see where it comes in a little bit later. There's the overflow bit. Overflow is kind of one of those unusual things. It's kind of like, what is it exactly? So overflow is something used for signed numbers, two's complement numbers. So remember, a single byte by itself, it's just a byte, just 8 bits. But you can use that byte to represent signed or unsigned numbers. If it's used as an unsigned number, that means it is a positive number from 0 to 255. If it's a signed number, that means it could be positive or negative, anywhere from minus 128 all the way to positive 127. Okay, and so 255 is really minus, what is it, minus 1? Anyway, yeah, so overflow. So the basic idea here is that if you have a two's complement number, and let's say you add some number in 2's complement that adds up to something greater than 127, then this overflow bit will be set, which is kind of like a carry, but it's for 2's complement numbers, for positive and negative numbers. So it's like a carry. Negative numbers, so this is for 2's complement numbers. If the number is negative, then the result is negative. Then that is in particular the first bit. So actually what this is, whenever you have any kind of arithmetic result, the end bit is actually the 7th bit in the result. So if it's a 1, that means it's a negative number. If it's a 0, that means it's a positive number, and it's used for 2's complement numbers. It has no meaning if you're working with unsigned numbers. It's the end bit. The z bit is the 0 bit. It's set if the result is exactly 0. Okay, and it's cleared when the result is non-zero. So anytime you do some arithmetic operation or some logical operation like ANDing 2 bytes together, if the result comes out to be 0, exactly 0, the z bit will be set. Okay, and then finally the carry bit. So the carry bit is used for signed numbers, for unsigned numbers. It's used basically for addition. So that's the S register. So the S register flags an arithmetic. When an arithmetic operation is performed, the processor doesn't know if the operation is on 2's complement or unsigned numbers. It doesn't know. Okay, so as the programmer, you need to know. Okay, and so the flags S, V, N, Z, and C can be used to clear up any confusion about what happens when you do an operation. So if you add 2 numbers together, and something happens, these flags can help you sort out what happened. Okay. So let's take a look at each of these critical flags in depth. Okay. So the C flag, again, it's used for unsigned arithmetic, not signed arithmetic. Okay. So it's used for registers that are values between 0 and 255, and they're assumed to be positive numbers or non-negative numbers. Okay, so the destination register and the source registers are assumed to be unsigned values. Okay, and as such, the C bit represents a carry bit, or it represents a borrow bit. So if you are subtracting 2 numbers that are both positive, and if the result comes out to be negative, then you actually have to borrow, and so then that bit is set. So that lets you know that when you do a subtraction, if that bit is set, that means you had to do a borrow, okay, from some fictitious bit. Okay, so here we go. For subtraction, if a fictitious 9th bit is needed to borrow in order to complete the operation, then C is equal to 1. For addition, this bit is set if the sum of the 2 bytes is greater than 255. So that's the C flag. Okay, so here are all the different flags. So this is the one we're looking at now. Let's move on next to the Z flag. Okay, this is in a sense the easiest one to work with. If the arithmetic operation or logical operation gives the result of 0, that is all 0 bits, then Z is 1. Z is 0 otherwise. So if the result is 0, then Z, you can think of it this way, Z is true. Okay, if the result is 0, Z is true. That is, Z is equal to 1. So it's easy to think the result is 0, Z is 0. No, it's not that. It's not like that. The result is 0, Z is true. That means it's 1. Okay, so that's the way you need to think of it. And the Z bit works for both signed and unsigned arithmetic. Okay, so that's helpful. So again, that's the easiest one to work with. The next bit is the N bit, and it's always equal to the 7th bit of the result. Okay, simply a copy of that bit. It reflects a negative number for a signed 8-bit integer. For example, an int 8t. Doesn't mean anything for an unsigned 8-bit integer. So, for example, a uint 8t. Okay, so that's helpful to know. Now the next flag is the V flag, and it is probably one of the more confusing flags to work with. Okay, it is one of the more confusing flags to work with. So here, these numbers P correspond to positive numbers, okay, and N's stand for negative numbers in this table, and then X stands for doesn't matter or don't care. Okay, so if I have two positive numbers and I get a P, a positive number, the V bit is 0. If I add two positive numbers together and I get an N, something's goofy going on there, I get a 1. Okay, so it tells me something goofy went on. If I add a positive number and a negative number, that will never give me something unusual. It just turns out you can't get anything really unusual that way. Okay, so notice this is again for signed math, and so you'll get a 0 because you won't get anything unexpected there. Because when you add a positive and negative, you could get a positive or you could get a negative. There's nothing surprising about that. If you add two negative numbers and you get a positive, something weird happened, and therefore you get a 1. So really, in a sense, the V bit tells you that something weird happened. Okay, if I add two negative numbers together and I get a negative number, that's not weird. If I subtract two positive numbers, it doesn't matter what result you get. This will give you a 0 because if I subtract two positive numbers, I could get a negative number. Okay, but again, for signed numbers, if I subtract two positive numbers, it doesn't matter. That number will always be between plus and minus 127. Okay, if I subtract two negative numbers, then again I will always get something between plus and minus 127. Nothing strange about that. If I take a positive number and subtract a negative number and get a positive number, that can happen. Nothing strange about that. If I take a positive number and I subtract a negative number, so remember that's like a positive plus a positive, and I get a negative, well that's goofy, and so I get a 1. If I take a negative number and subtract a positive number and get a negative number, there's nothing unusual about that. And finally, if I take a negative number and subtract a positive number, I should get something negative. If I get a positive, there's something goofy. So basically, V is the goofy flag. If you did an operation and you got a goofy result, that tells you something that the V flag will be set in that case. So the V flag is the goofy flag. Well, that's the way I look at it. Some people might take offense at that, but they're probably goofy too. Anyway, the S flag now is the sign flag, and it's always equal to N exclusive or V. So remember, V is like something goofy when happened, and N is the negative flag, or at least it's the first bit in that expression. So if this happens, it turns out that's actually associated with a sign, as complicated as it seems. So this is always used for signed tests. We'll come back to that in a little bit. It's simple to understand. That is, S is always equal to this. So once you know N and once you know V, once these are known, S is just given by that expression. So it's not so simple to discern what this result will be from the operation itself. So it's definitely more complex than V. And in fact, if we look at the table with V, I have to add a few more entries because now it matters whether it was positive or negative here. Okay? So here, in some of these, it didn't matter what the result was going to be. So for example, I took a positive, subtract a positive. It didn't matter what the result was going to be. I'm going to get a 0 there. But in terms of the S bit, it does matter. Okay? It does matter. So that's the situation. So the thing is, this basically always shows you when you got a negative result that you should have gotten as a negative result. Okay? So the S bit really shows you when you got a negative result that you should have gotten as a negative result. So notice, for example, here, you add two positive numbers, you got a negative number. that bit told you something goofy was up, but I should have gotten a positive number. And so the S bit tells me I should have gotten a positive number. See that? Here, I add these two together, I got a negative number. That gives me negative. Here I have two negative numbers, and there's something goofy that give a positive, something goofy with that, but I should have gotten a negative, right? Here I got a negative, I should have gotten a negative. Here I got a negative, I should have gotten a negative. So there's nothing goofy with that negative. So look at, whenever I see something negative and the result is not goofy, I will always get something in the S bit set. Here, if I subtract a negative number from a positive number, that's like adding two positives. I get a negative, there's something goofy with that, but the result should have been positive, so this is 0. So this really is like what the sign should have been in the result. Okay, so that's the sign bit. The sign. So even though it seems really complicated, it actually is what makes sense. The N bit and the V bit don't necessarily tell you what the result should have been, whether it was positive or negative. The S bit tells you. Okay, so that's the value of the S bit. Now, there of course are the other bits, but these are the most important ones for the arithmetic and comparisons. So now we look at the instructions that relate to comparisons, the most important instructions. First one is the compare instruction. Awesome instruction. Okay, I compare two registers, any two registers, okay, between 0 and 31. So it doesn't have to be just registers greater than 16. It can be any register. So I compare two registers, and basically what the operation does is it subtracts the two registers, RR from RD, but it doesn't change RD. That's nice. I guess it's like a free subtraction without changing the destination register. Okay, so I can do a comparison without affecting what happened in the destination register. That's awesome. Okay, but what it does do is it does affect some of the status register bits. It affects H, S, V, N, Z, and C. Yeah, actually the S bit is more important than the V bit. The V bit really, it's called the overflow bit, but really the important thing is the S bit. That's the sign bit. That's what the sign should have been. Okay, the V bit is not nearly as important, although it is useful at times. So that's the compare instruction. Okay, so what happens in branching is that you do a comparison. You know, for example, you do a comparison between two numbers, and then based on that result, you jump somewhere, you go somewhere, you go this way or you go that way. Okay, and so. But the first thing you need to do before you do any of those is you need to actually do a comparison. Okay, you need to somehow examine the two. And the CP is just one example. There are other similar instructions. Okay, for example, CPI. So this is comparing a register with some immediate data, where in this case the register has to be a register between 16 and 31. Okay, can't use the lower registers. But this can be any byte, so you can compare the two without changing RD. And once again, it does affect the status register bits. Okay, so the status register bits will be used in the branch instructions or the skip instructions. This is the compare with carry instruction. So the compare this is just like the compare instruction. That is, it uses registers between 0 and 31, any of the registers. So it does a subtraction, but it also takes into account the carry bit. Okay, and when you do this operation, you may affect these results, including the carry bit. Okay, so and it basically does this subtraction without changing RD. Okay, so but it does affect the status register bits. So that's the compare with carry. And finally, we have the test command. Test a bit. And basically what this test function does is it adds the register to itself. Okay? It adds the register to itself without changing the register. So basically, this is one way of testing whether a register is 0, basically. Okay? When you AND a register, so when you AND a 0 with a 0, you get a 0. When you AND a register with itself, you get a 1. So this could be used to test if a register is 0 or if this register is negative. So when you do this AND, if the negative bit is set, if the first bit is 1, this will give you an N. Okay. So it could also be used to give you a sign bit. Okay. Now notice that when you do this, V is always cleared. Okay. And so basically the sign bit is the N bit. Okay. V is always cleared when you do this operation. So actually V is affected, and the way it's affected is it's always set to 0 in this operation. So that's kind of an unusual thing that happens. So it's a testing for 0 or minus is really what this is. So less than or equal to 0 would be one way of looking at it. So that's the test instruction. Now, there are a number of branch instructions associated with the status register. So here are branch instructions associated with each bit of the status register. So the carry bit, you can see, has the most instructions associated with it. This instruction BRBC, notice it appears in every single one of these in these bits. So with the BRBS, branch if bit is cleared, branch if bit is set. Okay, so there's those same instructions apply to all the bits in that register. Okay, so otherwise we have some other things that are associated with various bits. Okay, and so that's how the status register affects branching. So the branch instructions then are used for branching. The next instruction is called compare and skip if equal. So basically it compares two registers and without changing the destination register and not affecting status register bits. This is like a miracle a miracle command. It compares two values, doesn't change the status register, and basically if the two values are equal, it skips the next instructions. It skips the next instruction. And usually what happens is the next instruction you have a jump somewhere. So this is a really handy instruction, okay? Because it can use any register. It doesn't change the destination register. It does not affect the status register bits. So it's a really nice command if you happen to need that kind of thing for a particular branching structure. So the important thing with branching is that you have to have an idea of what you want to do when you're doing the branching. As you've seen, there's a lot of different kinds of branching options available, but you need to know what you're going to do with that. Okay, you need to know what you're going to do with that. So just because this is a really nice instruction does not mean I will ever use it. It depends on the problems I'm trying to solve and what works best for the problems. I could always work around to use it, but then things just kind of get a little awkward. So no point in that. Awkward. Okay, don't need that. Okay, got enough awkward in my life. All right, skip based on some bit. So like the last command was a skip command. It would skip the next instruction, and generally, again, the next instruction would be some kind of a jump instruction. Okay, in this case, we're going to skip based on some bit. So in some register, if you have, if you want to check some bit in a register, say register, well, you have some register. Let's say you read in from port B, and in port B, you have some bit, say bit 3, that you read. Yeah, and you want to check, and if that bit is set, you're going to do this. If the bit is not set, you're going to do that. Okay, so this is a skip. If the bit is cleared, skip if the bit is set. Okay, so that's basically, so this is again nice. It uses any of these registers. Okay, does not affect the status register, checks whatever bit that is, and skips the next instruction. If the bit is set, that's the S, or if the bit is cleared, that is C. So how do these conditions now apply to some kind of an actual test, like if A is greater than B, if B is greater than or equal to A? How do we use those logical conditions that we would work with, and how would we relate them to branching instructions? Well, the answer to that question depends on whether you're looking at signed numbers or unsigned numbers. So that's important. Okay, so if we're working now with signed numbers, signed integers. So remember, if I have a byte that is signed, that means it takes on a value from minus 128 to 127. Okay, it takes in those values. Okay, so the value 128 actually doesn't work for signed numbers. Okay, so there's something about that. You need to keep track of those kinds of things. So it actually means something else. Okay, so here I have the different conditions that we could use. So for example, RA is greater than RB. Basically, that uses these status registers. Okay, if Z and S is equal to 0, then the branching will occur. So we can implement this using this command, branch less than. Okay, so less than, basically whenever you have these commands, the first one is whatever the second one. So RB is less than RA, okay, which is the same as this, it's just written differently. Okay, so keep in mind, so we've switched the R and A and the RB. So the complement of this command, RA less than or equal to RB, actually evaluates the status register this way, and it says branch if greater than or equal to. Okay, and again, RB and RA. So now if we do it this way, RA greater than or equal to RB, notice I don't have to swap the two. I can use them directly. And similarly, if I use RA strictly less than RB, I don't have to switch them either. I can use less. So notice it uses the same command, just a matter of what order you put the RA and the RB, the two registers that you're working with. Okay, so really these are the command you use: branch less than or branch greater than or equal, or branch equal. Okay, if you want it to test if they're equal. If they're not equal, then you branch not equal. Okay, so this is how the branching works for signed numbers. These are basically all the possible combinations that you would work with. Okay, so for signed numbers. Now what about unsigned numbers? For unsigned numbers, well, you have all the same kinds of conditions you'd be working with, but now you have a different set of commands. So notice I have branch if lower than, branch cc, okay? So branch sh, branch cs. So different. So basically, this is branch if the carry bit is cleared. This is branch if the carry bit is set. So these are branch if sh. I can't even remember what that stands for. But anyway, this is what you use if you want to test this with unsigned numbers. Notice that instead of having these two be the same, like with signed numbers, they're different. And similarly, these two are different. Okay. Now these two guys are the exact same as we have with the signed numbers. So equal is equal, regardless of whether it's signed or unsigned. But notice none of these commands are used for signed numbers. These are all commands used for unsigned numbers. So notice for unsigned numbers, we actually have more commands available for use. So that is how branching relates to these various conditions we would be concerned about. So that's the program flow of today's lecture. Now we're going to move on to timers and interrupts, inputs and outputs. I thought we did all that stuff already in the second unit when we were talking about all that stuff. Well, we did, and we're going to look at it again. So, timers, interrupts. They use all the same timer interrupt registers as in our SREG program. So, yes, that's the same thing. So, simple. We would basically follow the same procedures in setting up all the timers. We need to set their modes, their prescalers, their outputs, etc. Okay? Same. You need to set the exact same registers, same sequence. You can set these up either in C or assembly, whichever is easier for you. And I say you may become so comfortable with assembly that you might find it easier to do it in assembly. Maybe. Okay. if you get there, let me know. I'd be interested in knowing if you ever get to that point, because I mean, I'm your teacher. I'm introducing this to you, and if it becomes more comfortable, then that's good. That means I taught you something. I like to know that. All right. With interrupts, similarly, we have the same situation. So remember, often a time-critical code is in the loop part of the program, and so the setup routine can often be all in C. Okay, and interrupt service routines are often best handled in assembly. Okay, because again, they need to be short and sweet. They need to be fast, and also the interrupt service routine needs to use the correct vector, and the vector needs to be defined as a global. Okay, so this is important. So these are some aspects of doing these interrupts, setting up interrupts in assembly. Care also needs to be taken to preserve whatever registers you use in your assembly program. So in the part that goes with this lecture, the hands-on Arduino, you will see an example of this and what we do to preserve the registers we use. Basically, you pop them onto this stack at the beginning. All the important registers you're going to use, you pop them onto the stack at the beginning of your program, and then you push them onto the stack. You pop them back off the stack at the end of your program, and then in the middle of your program, that's your program or your subroutine. So, but you need to take care to preserve whatever registers you use. Again, the interrupt service routine could be interrupting right in the middle of some other operation. And so when it comes back from that operation, everything needs to be exactly the way it was when it left it. So inputs and outputs. The inputs and outputs, both analog and digital, require the same register settings as in assembly as in C. But there are some tricks. In assembly, the in and the out only work on I/O addresses up to 3F. But there are lots of registers, like some of the timer counter registers and so forth, that are above that, which is kind of weird. I don't know why they limited it, but it is. And but if you can use it, then use it, because these are actually faster than other ways of accessing the data. The next trick is if you need an I/O beyond 3F. Okay, so like timers or counters, again, lots of registers that are beyond 3F. Then you need to use LDS and STS. Okay, so this loads from static RAM. This stores to static RAM. Okay, and instead of using the I/O address, you need to use the memory address. Okay, so this is the kind of thing you need to work with when you're using LDS or STS. Now, if you include the AVR/IO.H header file in your assembly, then the registers are addressed using their memory address. So they're addressed using their memory address, not their I/O address. Okay, so their memory address then is of this form, and so you're good to go. And so you can always use the LDS and STS with the memory address. That's how they're used. Okay, even if you could use the in and out. However, I recommend that you use the in and out because they are faster. Okay, and so that speeds up especially your interrupt service routine. So tricks. There's a lot of tricks like this that were not obvious in when I first started doing a lot of this stuff, and you really have to read between the lines to catch things like this. Okay, so I have given you this information freely, and I hope you use it. So when I, for example, tried to do a project that involved something a little complicated, interrupt service routine, I started running into problem after problem. This doesn't work, and that doesn't work, and I couldn't figure out why these things weren't working. And it turns out there's this little thing like this that kind of messes you up, and and so forth, and they just kind of compound. So I'm giving you the fruits of all my experiments and studies, hours and hours, beating my head against these problems, talking to people, trying to find out information on the internet. You have the benefit of of all of this stuff. And so by summarizing it here in slides like this, you can benefit, and hopefully you can be more effective at designing codes in assembly language. So this is program flow, timers, and I/O. Thanks for watching.